I want to first thank again Jay Famiglietti and the Global Institute for Water Security for providing the technical assistance for this lecture series, Michelle, Mark, and many others. I also want to thank John Pomeroy and Global Water Futures, who underwrites this weekly seminar series this fall. Next week, don't forget, we have Steve Lowhide. Steve is a professor at the University of Wisconsin. He'll be talking about agricultural water issues and breakthroughs in ag water research. But today it's my distinct pleasure to welcome by WebEx Professor Barbara Sherwood Lollar from Department of Earth Sciences at University of Toronto. Barbara was set to come yesterday, but her son came down with pneumonia, and it was quite serious last night. He's seen a doctor today, got, I think, elevated meds, and is doing well today, and we hope to hear more good news from Barbara along these lines. But I really appreciate her her coming in by WebEx, because I know so many people were wanting to see her. So thank you so much, Barbara. A little bit of a bio on her. She completed her undergraduate in geological sciences at Harvard, followed by a PhD in the Faculty of Earth Science at University of Waterloo. After a short postdoc at Cambridge University, she became an assistant professor at University of Toronto in 1992, I think it was, where she's continued to this day, and now she is the head of the stable isotope lab there at University of Toronto. I first came across Barbara when I was chairing the AGU Fellows Search Committee. I was chair of the Hydrology Section Search Committee then, and Barbara's package was just incredible. Of course, she was awarded fellowship by AGU in 2015, and at the time she'd already had quite significant recognition. She was a fellow of the Royal Society of Canada. She had a Canada Council Killam Fellowship. She had an NSERC Stacey Fellowship. She was a National Groundwater Association Darcy Distinguished Lecturer, and many other accolades. But since 2015, she's really gone on to greatness in terms of unusual recognition for a Canadian scientist. She's won the Royal Society of Canada Bancroft Award. She's been an NSERC John C. Polanyi Award winner. Made a Companion of the Order of Canada, really a rare accomplishment for any Canadian. And in 2018 was the Geological Association of Canada Logan Medal winner, which recognizes really the highest level of achievement and sustained distinguished achievement in Canadian earth sciences. Barbara has over 150 journal articles and is really the international thought leader in ancient waters in the deep subsurface biosphere. Of course, like all good scientists, she used isotopes in her research, but unlike most isotope scientists, her impact on the field is unusually high. And it's just a real delight to have her with us today, even if it's by WebEx. And again, Barbara, we really appreciate you being with us under these trying circumstances, and we're all sending healing wishes to your son. Thanks very much.
Thank you all so very much. I really appreciate the collegiality and the patience that you've offered over the last couple of days. It's been extremely helpful to me. And again, I just regret not being there in person, but at least have the opportunity to engage with you today, taking advantage of there's some things that technology does very well for us, and in particular in these situations. So thank you for that. Indeed, what I'll be focusing on today is a combination, in some ways, a rather eclectic combination of hydrogeology, isotope geochemistry, and ending focusing on some of the implications of our understanding of the waters of this planet for the exploration of planets and astrobiology off this planet as well throughout the solar system and the universe. So thank you for coming along, and I hope this will be an enjoyable journey. Essentially, as you can see in the outline, we'll be starting by taking a look at the deep terrestrial biosphere and indeed deep terrestrial hydrosphere. But I will admit, and particularly as a Canadian, specifically focusing on the Precambrian lithosphere, and I'll explain why that is in a few minutes. And then looking indeed on what we know, a quick overview of what we know about water, energy, and life in the world's oldest rocks. And then in particularly focusing on the geochemical aspect of it, the role of water-rock reaction in sustaining life deep in rocks within the Earth, and the ways in which we use both searching for subsurface life and particularly noble gas geochemistry. And again, then ending up on this point about the implications of all of this for astrobiology. As I mentioned, I'm going to be talking about the terrestrial subsurface of the planet, but I'll make no apologies for the fact that, in fact, what we're going to be doing is focusing particularly on the Precambrian continents. We're very well aware of this in Canada, although sometimes it's less well known elsewhere, even at NASA from time to time. But in fact, the Precambrian continents make up the bulk of the continental lithosphere. They certainly account for over 70% of the continental lithosphere by surface area. And you can see that in the map that I show there, showing the areas in green, which are the covered Precambrian continental lithosphere, and the areas in blue, which are the exposed areas of continental lithosphere of the Precambrian, such as the Canadian Shield, for instance. But all in all, it does mean that the Precambrian continents do constitute a majority of the continental lithosphere by surface area, and even more by volume. And so hence they are a very reasonable place to be working if one is trying to understand something about the Earth writ large. In addition, of course, they are tectonically quiescent, and indeed this is one of the reasons why they're some of the oldest rocks on Earth. And indeed in our work from both Canada, Fennoscandia, and also the shields of South Africa, we've done a substantial amount of work trying to understand the nature of water and indeed life associated with that water in the Precambrian subsurface. How do we access these areas? Well, as we know, these Precambrian continents are not only the location of vast number of different active mining sites. So there are mine sites throughout the world, again, both Canada, Fennoscandia, and South Africa, where we've worked in order to take a look at this phenomenon of water in the subsurface. In addition to active mines, we can, of course, take advantage of underground research labs throughout the world, of which, again, there are a very large network. The one in Canada, of course, the Snow Neutrino Observatory, very well known, but a wide number of other subsurface laboratories that we know of throughout the world, many of them put in beginning in the 80s and into the 90s, in particular related to investigation for nuclear waste repositories. But other scientists, such as ourselves, are taking advantage of those access points in order to get places where we can go deep into the Earth to examine these phenomenon. And so specifically, I'm going to start with a quick overview of what it is that we know at this point in time from work not only by our group, but of course by other groups throughout the world, about water, energy, and life in the world's oldest rocks. This particular picture hopefully gives you a sense of the kind of phenomenon that we're working with. What you're seeing here is a picture from one of our sites. This is a picture actually from South Africa. This is from 1.8 kilometers below surface in the Beatrix Mine. And what you see there, gushing out of the wall rock, is a natural phenomenon. That's not mining water. That is very specifically saline water, a natural feature of the rocks that's retained within fractures in the rocks and then opens up. In this case, of course, it's released due to the excavation due to mining, but it's a natural process as well. Even away from mining, these fractures do open over time, and these fracture waters are released. On the right-hand side, then, you see some sense of what it actually looks like there. We've diverted it into a plexiglass container so you can get some sense of what it actually looks like. But the fascinating thing about this is that, in fact, this is something, a phenomenon that's very well known to miners throughout the world. If you spoke to miners in Zimbabwe or in South Africa, in Australia, in Finland, or indeed in Canada, they're very aware of the presence of these waters. And yet somehow it was something that had flown almost completely underneath the scientific radar until the 1980s. If we look into the annals of Canadian Geological Survey of Canada, there's references to this phenomenon back to the 1887 and 1888 annals. The gas and water are principally confined in large bugs or cavities and veins under great pressure. And yet again, until the 1980s, somehow this had largely flown under the radar of the scientific community, and it was really only in the 80s that this began to be investigated. So if these are naturally occurring waters, then what are the major characteristics of those fluids? Again, they do differ from site to site, obviously, but there are certain dominant characteristics. One is they are indeed highly saline. Indeed, in some circumstances, they are brines. Typically, calcium, sodium, chlorine dominated, and with total dissolved solids ranging from 50 to 250 grams per liter, depending on where you are. The temperatures there, of course, ranging as well, depending on the local geothermal gradient, with the highest temperatures we've encountered anyway within the rocks in South Africa. And water flow rates ranging from something on the order to 1 liter per minute. As you see on the lower right-hand side of this figure, it actually shows a plot of discharge over time from a couple of our boreholes. And you'll note that for some of them, the initial discharges are in fact very, very high. They can be on the order of 2 to 10 to 20 liters of water per minute. That does typically, though, deplete over time as the fracture waters drain, and typically the flow rates are more along the lines of the ones that you see there in the bullet points, about 1 liter per minute. Gas also exhalds from these waters because, indeed, they're very full of dissolved gases. And when that exsolution takes place, it can take place either very gently, such as in the picture you see here, or substantially more bubbling, typically, once again, on the order of flow rates of liters per minute. Now, for many of these phenomenon, the flow rates do, in fact, die away completely over time, and they're an ephemeral phenomenon. But in other places, including some of the ones that I'll talk about today, we've actually been able to monitor these kinds of flow rates of gas and water over a period of decades. So they really are a very macroscopic phenomenon, breathing substantial amounts of water and gas into the mine workings. What's in those dissolved gases, then? Largely reduced gases. These are typically very, very reducing fluids, and so not surprisingly, the gases that you find therein tend to be reduced gases. What this plot tries to show you is to compare the kinds of gases we find in these fluids to ones from the typical hydrothermal vents. So, for instance, in white are our samples from Kidd Creek Mine in Timmins, Ontario, Canada, and then in the open squares of the histogram are those from the Lost City hydrothermal vent. And so this plot is really here just to give you a sense of what's in these fluids. Indeed, they're very high in hydrogen. Indeed, like the hydrothermal vents at Lost City, these are some of the most hydrogen-rich environments on the planet, up to 10 to 15 to 20 millimolar dissolved hydrogen. In the pure gas phase, then, in the gas phase, that counts for, in some places, up to 50% by volume of that bubbling gas phase that you see, consisting of H2, hydrogen gas. The other reduced gases are predominantly methane, although with other substantial quantities of ethane, propane, and butane. So you can imagine if you have that much reduced gas, in particular that much hydrogen in these systems, there's a lot of interest in discovering whether or not, as we see at the hydrothermal vents, there's microbiology that's taking advantage of all of that hydrogen. And indeed, because I'm speaking mostly to a water group today, I won't focus a lot on the microbiology, but suffice to say that's a major driver of this research. And indeed, we do find globally throughout the world the association of subsurface chemosynthetic microbial communities associated with these fluids, taking advantage of those vast amount of hydrogen that you find there. Now, to date, our group and others throughout the world have done studies looking at dozens of different microbial communities down to about 1 to 1.2 kilometers. But there's still some fascinating horizons out there, and below about 1.5 kilometers down to 2 and 3 kilometers, there's still relatively few studies that have been characterizing the communities associated with those deepest, oldest, most hydrogen-rich fluids. In our own case, working with T.C. Onstad at Princeton and Esteban Herden in South Africa, we really only characterized fully 2 communities associated with the very deepest parts of these systems, but we're actively working on several others. So that gives you a quick sense, then, of the overview of the phenomenon that we're working with and this distribution of saline water, abundant reduced energy, and the presence of chemosynthetic life deep within the oldest rocks of the planet. My own particular role as a hydrogeologist and isotope geochemist is particularly to help characterize and understand the nature of the chemical reactions, the geochemical water-rock reactions that are producing the substrates that sustain the deep subsurface biosphere. And in particular, a lot of our work has been trying to understand that not only at the site-by-site scale, but also understanding on a global scale the contribution of these kinds of water-rock reactions to life on this planet. And so specifically, one of the key features of the work we've been doing was published about 4 years ago, where essentially what we tried to do was to pull together all of our own data from sites throughout the world, but also access a variety of different data published by other groups around the world, and really try to bring together in one document all of the data that we had for hydrogen and methane production within these kinds of deep subsurface fluids. So we have data here from more than 350 different samples from over 35 different sites around the world, and essentially it just illustrates the point that I made in the previous slide. If you take a look at the symbols, you'll see that each of the symbols represents the amount of hydrogen in the free gas phase. And indeed, it illustrates, for instance, if you take a look at South Africa or Fennoscandia, you can see the distribution of very high hydrogen-rich sites, particularly sites in which the dissolved gas phase consists of 10, 20, 30% hydrogen. But I draw your attention in particular to those sites that are represented by a yellow circle with a cross. Those are the really high hydrogen sites, the sites where we see hydrogen at the level of 30, 40, 50%. And if we translate that into a dissolved phase, that's millimolar levels of dissolved hydrogen. And indeed, as I mentioned earlier, some of the most hydrogen-rich waters on the planet. And as you'll see as we move through this talk, typically those are associated with a particular type of Precambrian rock, and in particular the ultramafic or mafic-dominated suites of Precambrian rock. And again, we'll talk more about that in a moment, but this gives you a sense of the distribution of that throughout the world. That hydrogen production, indeed, as I mentioned, coming from water-rock reaction. There's a wide variety of different water-rock alteration reactions that produce hydrogen as a byproduct, but the two major groups of that are illustrated here. On the left-hand side, I refer to radiolysis. Radiolysis is essentially the radiolytic decomposition of water that takes place as a byproduct of uranium, thorium, and potassium decay in the crust. As uranium and thorium and potassium decay, they produce radiogenic particles, of course, the alpha, beta, and gamma particles. And as those particles come into contact and attack the water, that actually decomposes the water and is a constant and consistent source of hydrogen within these rocks. And that takes place in rock types, irrespective of their geochemical composition. On the right-hand side, though, we illustrate something that's particular to, as I mentioned, these particularly mafic and ultramafic terrains. There we see hydrogen produced not only by radiolysis, but also by hydration reactions. Some of the most famous, of course, being the serpentinization reactions, the hydrate alteration of olivine that produces serpentine minerals. And as Canadians, of course, we're all familiar with serpentine. Of course, it is the famous soapstone that is used as a carving in the artistic work in the northern parts of this country, and indeed in Zimbabwe and South Africa as well. So there's actually a cultural manifestation of this wonderful water-rock reaction process that actually can produce hydrogen and sustain microbiology. At the time that we did that 2014 paper, what was fascinating is that these water-rock reactions were well known. They were an original work probably done by Ivan Barnes back in the 1970s and 60s. And what was interesting, and this is illustrated in the first three rows of this table, a calculation of the global contribution of this kind of water-rock reaction to hydrogen production had been done many, many times for the marine lithosphere. And so for the first three ones you see there were all done for ocean crust. Those are just three of the most iconic studies. There are probably another dozen more I could pull up. So this calculation has been done time and time again, considerable consistency in the calculation. They had all found, as you'll see in the third column, that hydrogen production from water rock reaction from the marine lithosphere, something on the order of 10 to the 11 moles per year. What was fascinating is up until 2014, a similar calculation had never been done for the continents. And so really part of our 2014 paper was simply to undertake that calculation. What did all this add up to on a global scale? And as you'll see in this slide, as we fill in the numbers from the 2014 paper, which I'll refer you to if you're interested in the details of how we generate these numbers, what was fascinating is that when we went to the continents, we found about the same thing, production of hydrogen on the order of 10 to the 11 moles per mil. So one way of saying that is we found that the continents were producing about as much hydrogen on an order of magnitude as the marine crust from these kind of water rock reactions. But if you think about it, in fact, what it means is by ignoring the continents, we were ignorant of half the production of hydrogen on this planet, of hydrogen by these reactions. So in other words, just by incorporating attention to the continents, we'd more than doubled the estimate of global production of hydrogen from these kinds of reactions that could support a deep terrestrial biosphere. And that has very important implications for habitability then, because it means that subsurface habitability is not driven by hydrogen and sustaining chemosynthetic microbiology is not something that's just associated with hydrothermal vents. It's not something that's just associated with the deep sea floor. But then, in fact, on a grand scale, the entire planet is habitable because these hydrogen-generating reactions are found deep in the subsurface, not just of the ocean and marine lithosphere, but the continents as well. And so in many ways, this was a really revolutionary way of thinking about the habitability of the Earth's continental crust. Having found this kind of hydrogen then, understanding that it's a global phenomenon and a significant phenomenon, then clearly a large part of the motivation of that was because of the work that we do with microbiological colleagues around the world then, who now come into these systems and try to investigate. The hydrogen may be there, so clearly these things are habitable, but is that hydrogen being utilized? Are these waters actually inhabited? And indeed, one of the strategies we use to do that kind of work, we sort of tongue-in-cheek adopted the NASA mantra for Mars, which of course was follow the water to search for life. And in some ways, we're doing something very, very similar, but applying it instead, in this case, to our own planet Earth. Speaking to a group that's very familiar with hydrogeological principles, a lot of what I'll be illustrating here is, of course, very, very well known. When we think about habitability, of course, we think first and foremost about the presence of liquid water, that life needs water to survive. But of course, as every hydrogeologist knows, the presence of water alone is not sufficient. In fact, what we need is the ability for that water to flow and mix on some sort of spatial and time scale. In sediments, of course, that means flowing and mixing in a porous media where advection and diffusion dominate. But of course, as we go down, and you see this illustrated in these various circles that illustrate the hydrogeological matrix, of course, as we go down into crystalline rock, we move into fracture-controlled systems, systems in which the water is primarily distributed within fractures within these systems. And indeed, as we get down into the kind of rock that we work in, very deep in the earth, these are systems in which those fractures may be highly disconnected from each other. We've entered a system in which you have a great deal of hydrogeological discontinuity. The fractures may be there, they may have water, but in some cases they may be connected, and others they may not. So it's not a big jump then to understand that when you're working in that kind of a hydrogeologically discontinuous system, the distribution of life will similarly be patchy and irregular if it's confined to those fracture waters. And as I'll show you in a moment, it's important to consider that as well as being spatially discontinuous, this also means that there is in fact a temporal discontinuity, because in fact these fractures serve as virtual time capsules. Indeed, the degree and isolation of those fractures, one from another, is a way of taking a look at these systems in the context of the degree and timing of the isolation of fluids and the life within. A way of understanding either whether they're still connected to the surface hydrogeological cycle, or indeed if they in fact have been isolated in the subsurface on geologically long timescales, and the implications that has for the nature of the microbial life found within. Because, of course, these fractures are not static. They do open and close as a function of changes in stress in the crust, even in the absence of active plate tectonics and geothermal activity. The stress of the continental crust alone cause these fractures to open and close. And, of course, because they're highly saline, they will often close up due to the precipitation of fracture minerals. So all of these processes mean that these networks capture fluids and gas of different provenance and different age. And by and large, as we go deeper and deeper in the crust, what we see is that the age or residence times of those fluids becomes older and older, ranging from thousands of years in the near surface to millions of years as we go deeper. And as we showed in our 2013 paper, in some very unusual places, we can even find fluids with bulk residence times on the order of 1 billion years. So indeed, this setting provides us with temporal variation in the supply lines for life. So far, in terms of the microbiology, and again, choosing what I would focus on for this audience, I haven't put a lot of the microbiology into this talk, but usually people ask me, what is the deepest microbiological system that your groups have so far characterized? And so far within our group, as I mentioned earlier, the most deeply characterized was the one done by Li Hong Lin and our group working with T.C. Onstad at Princeton, looking at a set of microorganisms in the Timmins Mine in South Africa within waters that had a bulk residence time of about 25 million years. And then we often get asked, well, how do you know those residence times? And, of course, the key tool that we're using there, with that kind of very pronounced age, of course, we're well beyond the ability to look at them from the point of view of something as simple as tritium or radiocarbon. We're actually having to employ the noble gas systems to understand residence times on this very, very extended scale. What I'd like to do, because I've been talking on very, very high-level principles about how we go about doing this, what our drivers are, and what our tools are. What I'd like to do for a moment is actually focus in on the Witwatersrand Basin in South Africa and specifically give you some sense of the way that this follow-the-water strategy has played out within the dozens of different systems that we've looked at in South Africa, again, done collaboratively with T.C. Onstad at Princeton and Esther van Herten at the Free State University in South Africa. Essentially, if we take a look at then the dozens of sites we've looked at, of course, there's significant variability from one site to another, but nonetheless, they do break down largely as showing us a system that's dominated by two hydrogeological and isotopic end members, essentially down to about 1.6 kilometers below surface. There we have saline fluids, but they're the lower end of our salinity spectrum, and they have temperatures sort of 20 to 40 degrees Celsius. Noble gas gives us estimates of their residence times that range on the order of thousands of years to maybe 1 million years. And as I'll show you in a moment, the delta-O18 and deuterium signatures of those fluids are very consistent with that. Delta-O18 and deuterium, of course, do not provide us with residence times, but they do provide us with important information about the time scale of circulation of fluids with the surface hydrogeological cycle. So I'll show you that in a minute. Deeper than that, below 1.6 to 3.3 kilometers below surface, this is where we get into our the real brines, the most high salinity fluids, the ones that are dominated by higher temperatures in the Witwatersrand Basin. And indeed, the noble gas provides us with confirmation that these fluids are also older within the Witwatersrand Basin. They tend to have residence times on the order of tens of millions of years, up to about 25 million years for that Mpenang site. It's here, too, that we see the highest levels of hydrogen associated with the most long periods of water-rock reaction. And once again, the O18 and deuterium are very consistent with that story. So with that overall scenario of what I'll do now is show you the actual data for those two end members within the Wits. Again, here we're showing you along the lower x-axis the delta-O18 signature, and along the y-axis the delta-deuterium signature for the waters themselves. The different symbols in different colors represent a number of different mines that we've worked in within the South African system. And what you'll see first is, once again, as I mentioned, down to about 1.5 kilometers there. Typically what we see is that the fluids, O18 and deuterium signature, fall nicely along the Harmon-Craig global meteoric water line, and indeed showing that these fluids still bear the signature of their recharge from surface. But you'll notice modern precipitation is very elevated compared to the mine waters, showing us that the mine fluids may be meteoric waters, but they're not modern meteoric waters. Instead, they're in fact paleometeoric waters representing recharge under past climatic conditions. And indeed, as I mentioned earlier, the noble gases pretty much confirm that story. We're seeing residence times on the order of thousands of years, up to maybe 1 million years, associated with these paleometeoric waters. Again, as I promised, as we go deeper, we see something very different. As we go down into the fluids that are deeper than 1.5 kilometers, down to about 3 kilometers, there you see this very dramatic pattern where the delta-O18 deuterium signatures of those waters fall way above the global meteoric waterline. Now, we're familiar with this. Brines in Precambrian continents throughout the world do fall well above the global meteoric waterline. They're one of the few kinds of hydrogeological systems that do. And typically that elevation above the line is a function of extensive water rock alteration. So consistent with the fact that these are the most saline fluids, the most hydrogen-rich fluids, their delta-O18 and deuterium signatures also bear the demarcations of that extensive water rock reaction. And indeed, once again, the noble gases are consistent with that as well, showing us that the residence times for these fluids are an order of magnitude older than the ones that sit on the paleometeoric waterline. And so for the Witwatersrand Basin in general, what we see is essentially mixing lines between these two systems, both of which are geologically old, but we see the paleometeoric waters down to about 1.5 kilometers, and then the most deeper and highly altered waters falling above the global meteoric waterline within the deeper parts of the system, and then mixing between these two end members depending on where you are within these systems. I've talked a lot about the noble gases, simply giving you the residence times. But obviously what I wanted to do in today's talk is give you some sense how we're actually using those noble gases to really give us better information about these very, very old systems in the deep crust. The noble gases are, of course, a wonderful part of the periodic table. These are the inert and conservative elements of the periodic table, and therefore ideal tracers. The beautiful thing about them as well is they come from three main sources: the mantle, the atmosphere, and then the radiogenic noble gases produced by water rock reactions in the crust. And happily, the end members for these three sources of the noble gases are both isotopically and elementally really well characterized. So that allows us then to evaluate systems using these three end members and the five conservative noble gases. To make it, I know there's a number of students in the audience as well, so I wanted to make sure I provided you with a nice review paper that sort of goes over this process of calculating residence times from radiogenic isotopes. The details can all be quite nicely found, in particular in this review by Bernard and our collaborator, Chris Ballantyne. But to give you a sort of schematic view of exactly how we go about this, essentially, as I mentioned, there are three main sources of noble gas, shown here in red, the mantle, in blue, the atmosphere, and in green, the crust. So essentially then, what we can do is we can use certain noble gas elemental signatures and isotopic compositions to identify the contribution of those different sources to the crust. For instance, then, if you're interested in a mantle-derived or magmatic component, you might take a look at, here in red, helium-3. Now, as I mentioned earlier, I'm going to make our lives much, much easier in this talk. We're working in the Precambrian continents. Most of these systems have no mantle contribution at all in modern times. And so for most of the systems that we're looking at, in fact, we see no contribution of mantle or magmatic-derived noble gas at all. And so really everything that I'll be telling you today is even a simpler story. We'll be looking at just the contributions from the blue atmospheric components and the green crustal radiogenic components. To draw your attention for a moment to the greens, these crustal radiogenic end members, indeed these are the noble gas isotopes that are produced by radiogenic water rock reactions in the crust. And so these are extremely important in terms of understanding the residence times of fluids or gas in the crust, because being produced by reactions in the crust, they accumulate in the groundwater as a function of time. And so by measuring the concentrations and elemental abundances and isotopic compositions of those noble gases, we can get a sense of how long that groundwater has been in the crust, accumulating those elemental tracers. For the groundwater component on the right, shown in blue, in noble gas we refer to this as the atmospheric component, and indeed often the air-saturated water component. In some ways it's a little bit confusing, because how does the air get into the subsurface? Well, of course, it gets in through groundwater recharge. So although throughout this talk I will refer to this as the atmospheric or air-saturated water component, you might better think of it as the groundwater recharge component. In other words, the component that shows you the contribution of groundwater that's recharged from the atmosphere. And so as I mentioned then, in our system, we'll be looking largely at the blue and the green, a simpler system of two-component mixing between groundwater that's been recharged and the contribution of crustal radiogenic noble gases that build up over the time that that groundwater sits in the crust. In addition, although we do measure and use all of the suite of noble gases, I'm going to start first by just focusing in on one system, and that is the neon system, to make it a little bit simpler. And so what I'm going to do is go back to the Wits-Watersrand Basin, go back to that scenario I showed you of the two paleometeoric water and deep brine end members, and we're going to look specifically at the data for the neon isotopes. Once again, I'll recall at the top the first bullet, the mantle-derived components are in fact negligible in these systems, so we're really going to be looking at data that can be explained by mixing between two systems, between the air-saturated water system and then the radiogenic contributions as that water sits in the crust. To look at the data then, we're going to start first by looking at those paleometeoric waters, the less saline end members, the ones that we find down to about 1 to 1.5 kilometers. And we're looking then at the 21/22 neon isotopic signature on the x-axis and the 20/22 neon on the y-axis. And what I can tell you is that to a large degree, shown here in the blue diamonds, The Paleometeoric waters of the South African basin look like a textbook, classic poster child of radiogenic air-saturated water mixing. As you can see, the data starts at the air-saturated water, the atmospheric recharge end member, and then moves off nicely along this line in the direction of the average radiogenic crust end member as these waters accumulate radiogenic components from the crust over time. The slope of that line varies a little from place to place around the world, but by and large, until we did this work, anywhere in the world that you measured this kind of a system, this is exactly the kind of mixing line you got. The surprises began as we moved deeper in this system, and I'll show you that on the next slide. As we moved into those deeper waters, the highly saline ones, the ones with all the hydrogen, the ones with tens of millions of years residence times, we saw something that had never been seen before. We saw the data that you see here in the yellow diamonds. These were neon isotopic signatures that didn't sit anywhere near to what anybody had seen before in the crust of this planet. They were, in fact, the most elevated 21 over 22 neon signatures ever identified. And to try and explain them, we had to take another step. We decided to actually take a look and analyze some of the fluid inclusions from the Kopval craton. And when we measured those fluid inclusions, those are shown here in these circles, and then also some additional data run by Kendrick et al. Later from actually the Yilgarn craton shown in triangles. And what you see here is that for the very first time, we'd actually identified flowing water in the subsurface that had isotopic signatures similar to those of fluid inclusions within the host rock, and indeed falling along a mixing line between them, showing us that the neon that we're finding within this water has an isotopic signature similar to those of these primary fluid inclusions. Now, the primary fluid inclusions in this setting are remnants from the last major metamorphic event. In other words, then, we're seeing in the flowing modern water remnants of the last major metamorphic fluids and the neon associated with that. So this was incredibly exciting. It's never been seen before. And I should add as well, the most radiogenic noble gases that had ever been seen right across the board. Again, I'm focusing primarily on neon, but right across the board, neon, helium, argon, xenon, these were all the most radiogenic end members that had ever been measured. The key thing to emphasize here, though, is although the neon is 2 billion years old, now we have to move back to the bulk water residence time, and you'll recall that I told you the bulk water residence time for this, for the oldest fluids here, is on the order of 25 million years. So again, the neon is the most conservative part. It's telling us about the oldest contribution to that fluid, and that is indeed more than 2 billion years old. But the water itself is on the order of 25 million years. But what was nonetheless exciting about this is that indeed up until this point, of course, as geologists, we've all known that ancient fluid and gases can be trapped within rocks on a microscopic scale from the time of their formation. But really, this was the first time that we realized that there were, in fact, macroscopic samples available to us, too. And that at some of these sites, in fact, macroscopic scale, we have available to us, in fact, liters of fluid in which some of the noble gas and most conservative end members actually provide us with billion-year-old samples. And so that's an extremely exciting aspect of this work. It's not one that I'm going to focus on in more detail today, although that is an exciting part of the story. What I want to do is to continue to follow on this idea of follow the water. Because the next thing we did was to take this whole team, and the first thing I did was to persuade them to come back to Canada with me, to come to an area of the Canadian Shield where we worked for many, many years, the Kidd Creek Mine in the Superior Province in Timmins, Ontario, as you see here. There are a number of very compelling reasons to bring the team to Timmins. One of them is this is the deepest base metal mine in North America at this point in time. Essentially, the Timmins Mine, the Kidd Creek Mine, is now operating down to almost 3 kilometers below surface. So it's as deep as the South African systems. But what's fascinating about the Kidd Creek system is that it is a, they always say for the Archean rock, it is relatively well preserved. It has undergone relatively low thermal history. And certainly the thermal history of the system shows that essentially the last regional metamorphism was only to green schist phase. It peaked at about 2.6 billion years and then has essentially been cooling ever since. This is a system in which the pillow lava structures are actually still preserved in the wall rock. So this is a site that would be the perfect target to go to try to understand just how long fluids could be preserved in the crust and just how old the noble gases associated with those fluids might be, because it's really a prime example within Archean rock of Archean rock that has been least metamorphosed, least disturbed. And so indeed what we did there was working at the 2.4 kilometers below surface. We had a series of fracture networks there that we were able to sample and monitor over 12 to 15 months. The details are in the paper here, so I won't go through the details in huge. This gives you some sense of it, though. I'm going to start first with, again, to keep it simple, with the neon stories. And I'm showing you again only exactly what you saw before. This is once again just the distribution of neon, and once again just from the Wits Watersrand Basin, showing you again the paleometeoric water in blue, classic radiogenic neon, and then the elevated signatures that we found in Witwatersrand Basin that were our first indication of these incredibly old preservations of ancient noble gases in those fluids. What I want to do now, though, is show you, overlaid on top of that, what we found at Kidd Creek. And indeed, what we found at Kidd Creek is shown here now with data in the square, yellow squares. And this was extremely important to us because, of course, what it shows is that that unusual neon signature is not unique to the Witwatersrand Basin. It's associated with rock of the same age within the Canadian Shield. Once again, in this case, as you can see, we're even farther out along this mixing line. We actually have flowing fluids, once again, whose neon isotopic composition is similar to those of the ancient primary fluid inclusions. Breaking records yet again, these were the highest radiogenic neon and argon ever reported in free fluids. If you're a noble gas aficionado, a 40 to 36 ratio of over 44,000. Again, attesting to just how long these waters must have been sitting in the crust to accumulate these very, very rich radiogenic compositions. In terms of what that means for global gas residence time, again, we have a large amount of data within that paper. Rather than go through it all in detail, I'll refer you to the paper and just take you to the punchline. The key issue is when we then translate this into noble gas residence times for these fluids, and when we do so for these four independent noble gas systems, for the radiogenic helium, neon, argon, and xenon. No matter what we do, the residence time for these fluids are all more than 1 billion years in age, ranging from 1.1 to 1.6 billion years, and consistent across all of these different lines of evidence. And of course, this very much transformed our understanding of just how old flowing water could be, and just how old and how long the conservative components of those flowing water could be maintained in the crust. I just showed you 4 independent lines of evidence. I'd like to emphasize that this paper actually has 9 independent lines of evidence, and that's a really important story to send out to the students out there. We waited 4 years to publish this paper. We had initially 7 lines of evidence, and 6 months before we submitted, we decided to go back and measure 2 more things. Something that is this game-changing, we felt, had to have as many lines of evidence as possible, and we were in no hurry to rush to publication. We wanted to make sure that we had as many lines of evidence as possible to support this kind of interpretation. So I think that's a really important lesson to get out there in a time when we sometimes feel that there's this pressure to rush out and publish everything immediately. It's really important to get all your ducks in a row and make sure that you have multiple lines of supporting evidence. So in addition then, in the paper, in addition to that first bullet that we just went over, the noble gas evidence from the helium, neon, argon, and xenon, there's a variety of other isotopic evidence. I won't go through it in detail. It's related to things particularly within the xenon isotopic composition. But the one that I will flag for you is once again related to the O18 and deuterium system that we talked about earlier. And so the picture on your left there, once again, shows something that we discussed in detail earlier, the O18 and deuterium. Some of the data from some of the other sites around the world are shown there, but in the open blue squares are the O18 and deuterium data for the same waters for which we just looked at the noble gas residence times. And you'll see how far above the global meteoric waterline those sit. So once again, the O18 and deuterium are also consistent with extensive periods of residence time in the crust, extensive water rock alteration. They're the most elevated O18 and deuterium signatures that have ever been seen. And indeed, they should be if they've got this kind of radiogenic noble gas signatures as well. So all of these lines of evidence coming together to support the antiquity of these fluids. We've gone deeper yet. Over the last year, we've actually been able to sample down at 9,500 level, almost 2.9 kilometers below surface, in the work of Oliver Rohr, who's a postdoc in my laboratory, who's essentially just published this and a number of other papers that are about to come out. Again, I won't go through that in great detail. Suffice to say that the waters down at 3 kilometers are even older yet, and some of these push the residence times back to about 2 billion years for these deepest parts of the Kidd Creek system. What I want to do now, though, is I want to correct the impression that what we're doing is running around the world just trying to break records and find the deepest, oldest, most preserved. And that's fascinating, and indeed it is part of what we're looking at. But really, the mindset here is different. The mindset here of what we're trying to do is actually to be very systematic, to take a look at these deep subsurface sites in Precambrian cratons throughout the world, and to try to understand the whole spectrum of water residence times within these systems, ranging not just looking at Kidd Creek, where we have these very, very oldest, but also, as you'll see on the left-hand side, we are very interested as well, as we saw earlier, in systems within South Africa where we see meteoric or paleometeoric end members and waters with residence times that are only tens of thousands of years. And indeed, we're interested in the whole spectrum. Because as I emphasized earlier, a big driver here is not just geochemical and hydrogeological, but the search for life within these systems. So in fact, the reason to understand the residence times is so that we can understand constraints around the kinds of life that we find. And so it is equally fascinating to us to take a look at the Driefontein mine, for instance, in which the waters are hundreds to maybe a couple of thousands of years old. We see paleometeoric waters, and in addition to seeing microbial life, we in fact see nematodes and eukaryotes that are in fact feeding off of the microbiology. And that's fascinating to us. These are indications of deep subsurface systems, but systems that still have, within 10,000 years, connection to the modern hydrogeologic cycle. We're interested, of course, in the ones that fall in the middle, the ones that have resonance times on the order of tens to hundreds of millions of years. And I mentioned the work of Lee Hung Lin earlier in the Empening mine in South Africa. And then finally as well, we are indeed working on these very ancient systems, the ones of the Kidd Creek, and we have evidence of life within these systems, and that's currently in publication. So there's life throughout these systems. We're interested in all of that life. But again, in the interest of time today, rather than focus on the microbiology, I just wanted to end with just the last couple of slides to give you a sense of what all this means beyond Earth, and indeed for astrobiology, and its future directions. The future directions that I've emphasized, of course, have been around this idea of understanding preservations of fluids and noble gas components, novel samples of ancient fluids, and this question of habitability in the Earth's oldest rocks, what is actually living there and taking advantage of all of that water-rock reaction. But a very large component of this as well is related to understanding fracture-controlled water-rock reactions in subsurface life in the context of astrobiology. We've seen a lot of work on this planet in the context of trying to understand the search for life elsewhere. I love this slide because it really describes a little bit why we need to do that. If we think back, for instance, to the early investigations of the Martian surface, of course, most of those were indeed surface examinations. And this particular slide given to me by Mike Carr, who was, in fact, one of the chief scientists on the Viking expeditions, just really encapsulates it. Those were geological investigations and missions. They were terrific, but at that time we were not thinking about the subsurface. But at this point in time we are. We now understand much, much more about subsurface life, not just on Earth, but in fact, as we've been seeing just over the last summer, I've thrown in here 3 different papers that have come out just over the summer, all of which speak to an evolving and expanding understanding of subsurface processes on Mars. We see the evidence from the Webster paper of methane in the Mars atmosphere, which requires subsurface processes, potentially subsurface processes of water-rock reaction that produce hydrogen and methane in the same kinds of rocks that we're looking at on Earth. We've seen this identification of liquid water in the subsurfaces of Mars. We've seen in other studies the identification of the ocean worlds of Europa, the plumes of Enceladus, which are essentially plumes of subsurface material produced by water-rock reaction that are exiting from the south pole of the moon of Enceladus, and of course the discovery from Kepler and other missions of the exoplanets and the vast number of exoplanets potentially in the habitable zone. All of this work is focusing our attention on subsurface environments, but also subsurface processes. So although we may be working in the Canadian Shield, the implications of these are very, very strong for astrobiology. And all of this very much on my mind because this time last week, of course, I had the great pleasure of chairing the National Academy's recent review on the astrobiology science strategy for the search for life in the universe for NASA. I had the great pleasure of serving as the chair of this committee, but with 16 outstanding colleagues, and our job was to take a look at the landscape of discovery, technology, and intellectual development in astrobiology. There's a lot in that report if you're interested in it, but the part that I think really speaks to hydrogeologists is this one. One of the major themes in that report was simply making the point that in light of the exciting discoveries that I've just gone over with you, the exciting discoveries about the subsurface of the Earth, Mars, ocean worlds, and exoplanets, that astrobiology needs to continue to build on that, to really focus on our understanding of subsurface processes and subsurface environments for life as we investigate not only Earth, but go outwards in the solar system and indeed the universe to take a look at astrobiology. So with that, I'd like to wrap this up because I'm cognizant with the problems we had at the beginning. We're running a little late. And so I'll stop at this point then, just acknowledge the large number of people who contributed to the work that you saw here today, and I'll be happy to take any questions.
Great. Well, thanks very much, Barbara. That was really a thrilling talk. We've got students here from the class who read your paper earlier today. They're ready with some questions. We've got Grant Ferguson, Bruce Eglinton, and a few other hydrogeologists here I hope also will be ready with a question or two. And we've got a few minutes to maybe field a few of these while they're thinking of their questions. I wanted to talk just about the hydrological implications. You know, everyone in Canada in grade 11 or so learns about the hydrological cycle: evaporation, condensation, you know, precipitation, recharge, and around it goes. And in addition to the many other fields you're impacting, man, you're really rocking our understanding of the water cycle. And I'm wondering if you have kind of a sentence to maybe characterize your new description of the water cycle, something you'd tell an 11th grader who's maybe come home with homework related to the water cycle, and how you would maybe twist it to describe or include the things that you're finding.
Yeah, well, I mean, it's like bringing coals to Newcastle with you guys. As you know, part of the reason I wanted to come was because of the outstanding work that you folks are doing at Saskatoon related to exactly this kind of issue. There's some great work that's been done as well in Canada by Tom Gleason and others, estimating, you know, the amount of groundwater associated with the canonical cycle, the one that's in contact with the surface. But what we're showing, and indeed the Warrenall paper has some back-of-the-envelope calculations we've initially done, to try to calculate how much is this water that is not, in fact, cycling with the surface cycle, at least on any kind of a modern time scale. I've been calling this the hidden hydrogeosphere, because obviously it's there. It is cycling or interacting on some level as these fractures open and close, but it's on a spatial and a temporal time scale that is distinct from the surface cycle. There are certain fluids down there that have not been in contact with the surface cycle, clearly on geological time scales. And so when I describe this, in fact, to 11th graders, as I often do, because I do a lot of work in the schools, what I try to do is to say, visualize this as if, you know, you had a flooded basement. The waters came in, flooded up your basement. You've had to pump them out. Those were the easy ones to get rid of. That's the quick cycle. Then you had to swab out with a broom and a mop the stuff that was sort of hanging around in the closets and then the corners. That's the older, deeper cycle. But then after you think it's dry, what you didn't realize is how much of that water seeped into the cracks in your foundation. You can't see it anymore. You may not even see evidence of it anymore, but that moisture, that water has seeped down deep into the cracks. And in fact, years from now, the potential damage from that water may be evident in your home. And I think it's a gross analogy, but perhaps it's a rather vivid analogy to try to understand how it is we can actually reconcile these different ways of thinking about the hydrogeological cycle on different scales and different scales.
That's great. I might just borrow that next time I'm talking to an 11th grader or a PhD student for that matter. In class, Cobb, maybe grab the microphone. Mark's got it there.
Hi, thanks for your talk. I'm curious about, you have the opportunity to gather this data in a handful of sites that give you access deep into the crust, and I'm curious what you might expect to find as your access to more sites grows, or if our access to more sites grows. If we, do you anticipate, or do you anticipate that you would, going down to the same depth, somewhere else on the planet that we don't yet have access, we would find the same things, or that there are processes that might, deviate from what you've already found?
Good.
Thank you. It's actually a really good question, because really what you're asking is what are our hypotheses that we want to test as we go forward with this? And some of that's happening already. I mean, as we move from South Africa to the Canadian Shield, the hypothesis was as we go into rocks that are really well preserved, will we see the same phenomenon that we saw in South Africa, and will in fact be an older manifestation of that? And indeed, it turned out to be the case. And now as other people around the world are looking at other well-preserved sections of cratons, they are coming up with similar kinds of ages and similar kinds of observations. So it's really nice to see that confirmatory kind of approach is taking place. But in addition, one hypothesis, for instance, that we asked ourselves was, what if we go to craton that's of a similar age as the Kidd Creek system, but craton that we know has been very disturbed? For instance, blasted by a major comet 1.8 billion years ago. So indeed, specifically, although I didn't highlight it in the talk, you'll see in that one slide, and you can see it as well in detail in the War et al. Paper, we went back to Sudbury, where I'd worked for years. So we knew the fluids were there, we knew the gases were there, but we went back to do the residence times. And specifically, we went into not the 1.8 billion-year-old rock, but we went into a couple of the mines that are actually in the Archean basement underneath, in rock that's the same age as Kidd Creek, but of course has been highly fractured and disturbed, particularly by the fracturing associated with the impact in the Sudbury Basin. And indeed, we hypothesized there that we would see old waters, but not as old. And if you happen to be quick-eyed as I move through that slide, you'll see that the kinds of signatures we got out of the Sudbury Basin were on the order of 300, 400, 500 million years. So again, a nice verification of that hypothesis. So indeed, there are places around the world where we're particularly targeting, both to try and take a look at where ancient fluids are likely to be preserved, but also, frankly, to understand where, although we might have ancient rock, we might expect younger fluids. Because again, for the life question, we work on the assumption that any life we find down there is not a second origin, right? It's going to be related to other life on the planet. So how did it get down there? It must have colonized the subsurface. So we're also interested in those places where the rock may be old, but the fluids may be younger, because that'll give us, again, some sense of when and how some of that life entered into these deep subsurface systems.
Great, thank you. I'm sensitive to time because we've gone a little bit over with some of our technical issues, but just looking for another last question. Grant, yeah.
Good to finally get a chance to talk to you this week, Barb. So we connected eventually. So I guess my question comes down to mechanisms. As someone who's more of a physical hydrogeologist who dabbles on the chemical side and tries to work with as many people like you as I can, why do we see, I guess, the 300 million year old age at Sudbury is kind of a head scratcher, because we don't see a regional flow system in that area like we would, say, in some of our sedimentary basins. So do you have thoughts on why we see those differences?
Yeah, I mean, these are systems that are not really within the regional flow systems at all, right? They're older than that, and I think that's why. So these are, we know from the noble gases that some of the components of these systems are, in fact, at least at Kidd Creek, as old as the rocks themselves. So some of these components at Kidd Creek, anyway, actually represent ancient seawater or ancient atmosphere from the time, and then mixing with what might have been regional water, but way, way back. And so one of the best ways, I do have one more slide that might pop up, because one of the best ways I have found to try to think about this, and then in fact the reason why, Jeff, Grant, and you guys, I come knocking at your door is exactly, I hope through collaboration with the physical hydrogeology, for the people looking at the distribution and spatial and temporal distribution of porosity and permeability in the crust, will help us begin to elevate these models to a larger level. But, I mean, the best thing I've come up with to think about this has to do with these kinds of figures, where you take a look at sort of the stochastic understanding of the distribution of water in the crust. And if you take a look at this sort of idea of these discrete storative elements, there is always one node that, no matter how well we fractured the system, doesn't get fractured, doesn't get opened. Sometimes it's referred to as the sugar lump idea. Well, in some ways, what we found at Kidd Creek may be the ultimate sugar lump. And so, indeed, by taking a look at the probabilistic distribution of fracturing within these systems, we may be able to understand some of the controls on these residence times. At least that's my hope.
Thank you very much. I want to thank Terry and his team for Herculean efforts pulling this off, but of course, first and foremost, Barbara, for not just a great seminar, but for sticking with us today. We're so glad your son's on the mend, and we all wish him well. And on behalf of the group here and the many hundreds watching either live or on tape delay via YouTube, I'd like to thank you for such a compelling seminar. We hope to have you here in Saskatoon one day in the future. Thanks very much, Barbara.
Looking forward to it.